In this subtopic 2.3 work, energy and power, we can consider this as basically being a combination of the previous two subtopics on motion and forces. We'll start off first of all by looking at work and what work is in a physics sense. So in physics, work is done when a force is applied to move an object. So you can see there dealing with forces and dealing with motion in the moving of an object. So combining those two ideas. Now we can calculate work by considering that distance and the force. So the distance that the object moves. So first of all, considering that distance, and need to be clear here when we're looking at the force that's causing that motion, we need to consider the component of the force that is in that direction. So it's not the total force, it's the component of the force in the direction of motion. So if we look at an example here, let's say we've got a box that's sitting on the ground and a force is being applied in that direction. So there's our force, and that force causes the box to move to some new position. If we use this edge here as our reference point, that would be the new displacement of the box. And notice here that we have an angle between the direction that the force is being applied and the direction of motion of the box. So here the work is equal to the magnitude of the force multiplied by the distance, and we've got a cos theta term in there. So you can think of that as being, if you look at F cos theta, so combining those two terms, that gives you this component of the force that acts horizontally in this scenario. More generally, it won't always be a horizontal force. It might be a force that is being applied vertically or in other directions, but we always need to consider the direction of the force that is in, the component of the force that's in the direction of motion. Two other things that are important to note here. Some special cases of where no work is done. And the first one, if we have theta being equal to 90 degrees, so when theta is equal to 90 degrees, that basically sort of like a normal force, for example. A normal force won't do any work on an object if it's moving horizontally. So the normal force, say, imagine an object that's sliding along an ice surface, say a car, for example. The normal force won't do any work on the object because the car is moving horizontally while the normal force is acting vertically. And secondly, if the displacement or the distance that the object moves is 0. So that would be, say, standing there holding a box. As you're holding the box, you might still be applying a force to it so that it doesn't fall, but because there's no displacement, then technically you're not doing any work on the box. Now the units of work, the quantity of work, we need some units to measure it. The units of work are measured in joules. So joules, the symbol has a capital J, and 1 joule is the work done when a 1 Newton force moves an object by 1 meter. As an example, so a way to sort of put this into context, that would be like lifting a 1 litre bottle, or about 1 litre of water 1 meter into the air, so around about that, roughly speaking. Hopefully you can see here as well, if we're applying a force of 1 Newton and moving it by 1 meter, we have an equivalent unit here. So we can talk about joules, but we can also talk about Newton meters. So 1 joule is the same as 1 Newton meter. So that's about work. Let's now look at how work and energy are related. It's a fairly simple explanation here. It's basically just that when work is done on an object, energy is gained by, or the object gains energy. So do work on an object and the object gains energy. So you might then think, well, okay, what exactly is energy? A little bit of a circular definition here. Energy is simply the ability to do work. So the ability to be able to apply a force to an object to get it to move over a distance. So that's the easiest way to define it. And it comes in a number of forms. And the most common ones, the ones that we're going to focus on mostly here, are as follows. So the first is kinetic energy. And kinetic energy is basically the energy of motion of a mass. So that's the first fairly common type. The second is gravitational potential energy. And hopefully these terms are familiar to you. You should have covered these in perhaps Year 9 and Year 10 science. And gravitational potential energy is due to the position of a mass in a gravitational field. And the third fairly common type that we're going to refer to here is elastic potential energy. Sorry, spell that correctly. And elastic potential energy is the stretching or compressing, depending on the type of object we're dealing with. So the stretching or compressing of an elastic object. Now, what I mean by an elastic object is an object that will return to its original dimensions once the force that has stretched it or compressed it has been removed. So a spring, for example, you stretch a spring and it'll return to its original position. Something like, say, a lump of clay wouldn't be able to store elastic potential energy, because once you've deformed the clay, it doesn't return to its original position. So those three forms there are the ones that we're going to focus on throughout this unit. We'll develop those ideas in much more detail. There are other forms as well, such as chemical potential energy, nuclear energy, electrical, heat, light, sound. Lots of different forms, but ultimately these are the three that we'll focus on as we move forward through this unit. Now, since we said that energy and work are basically the same, energy is also measured in joules. So if you do work on an object, it gains energy. So the units of both work and energy are joules. Fairly commonly, we won't just talk about joules. 1 joule is actually quite a small amount, as I mentioned before, with the 1 litre of water being lifted 1 metre. So you'll often talk more about kilojoules or megajoules rather than just the unit of joules themselves. One last thing to finish this video off. Energy can be, it doesn't just sort of exist in one state and that's all. Energy can be transferred between objects. And an example of that would be something like kicking a ball. So in that case, the kinetic energy of your foot would be converted to kinetic energy of the ball, or transferred to kinetic energy of the ball, or energy can be transformed. And what we mean by transformed is that it changes the type of energy, but not necessarily changing between objects. So an example there would be something like a bungee jumper. So initially a bungee jumper would have gravitational potential energy because they're raised a certain height in a gravitational field. As they jump off, the gravitational potential energy is converted or transformed into kinetic energy, and then as the bungee jumper continues to fall, that the bungee cord will start to stretch and the kinetic energy is transformed into elastic potential energy. Now, in all energy conversions, the law of conservation of energy applies. And that basically states the following. So that's a fairly important law in physics. A couple of different ways to think of it. The first is that energy cannot be created or destroyed. And as we've just said, it can be transferred or transformed. Usually the way that this will be defined is something like energy cannot be created or destroyed, it can only be transferred or transformed. Won't bother writing that again since we've already jotted those notes down. A second way to think about it is that the total energy before an event is equal to the total energy after an event. So what do I mean by that? If you think about the example I mentioned earlier of kicking a ball, the instant that, or the instant before you kick the ball, all of the energy would basically be kinetic energy of your foot. As your foot is in contact with the ball, energy is then transferred to the ball. The ball will then start to move, and so all of the total energy after you've kicked the ball will still be the same amount. Yes, some will be lost to heat and sound as your foot is in contact with the ball, so you then need to consider the kinetic energy of the ball, heat energy and sound energy, add them all up, and that would be equal to the initial kinetic energy of your foot. So we'll have a look at these ideas in a little bit more detail in class. We'll look at some energy transformations and where energy is transferred and transformed, and as we move forward we'll then start to develop equations around these ideas as well.